So that's your problem number 4.
No, they are rejected.
You can choose a random flavor.
Okay, you have only 30 minutes.
Okay, we accept the challenge.
Okay, presenter, please write down your name on the blackboard. Preparation of the recorder. Oh, someone is coming to fix it. 多久啊？多久？
设备有问题的是要通知那个。
有，我们请同学来处理了。
不用接，都是自动感应，就赶快把它接好，大家就会感对啊。 昨天我们有那个记者马上跟我来看，食物进口会减少，他们在投资这样这个。
我是从另外一边来的吧，从另外一个 building 过来的，从西安那边来的。
你有试过其他电脑飞吗？
那种叉3的。
在哪里？
再过来了。
这边所以这边都没有半个人哦，应该要有一个人，所以你们就只有一个人吗？一个人到处跑吗？嗯。
开始要推。
Sorry. I have.
还有。Yeah, let's wait for the clock.
Ready?
可以了吗？
可以。
Reporter, are you okay? Already?
No.
Sorry. Oh, I'm ready.
Okay. Presentation of the reporter.
Okay. Hello everyone. I'm the reporter from Team Bernoulli, and I'm here to report number 4, timing magnets. And about the problem statement is attach a rod assembled from cylindrical neodymium magnets horizontally to a vertical ferromagnetic rod and limit the motion of the magnet to the vertical direction. And when the ferromagnetic rod is spun around its axis of symmetry, the magnetic rod begins to climb up. So explain this phenomenon and investigate how the rate of climbing depends on the relevant parameters. So to my focus point, first is how the magnet climb up. So I will introduce the mechanism between the climbing magnet and the rod. And second is what parameters affect the rate of climbing. So I will do some experiment of changing different parameters to see how it affects the rate. And I will use tracker to track the motion of the magnet to see how it goes up and how it climbs up. And as you can see, the trajectory of the motion is not a linear line, so I assume that there is some phenomenon between the magnet and the rod. And I also do the experiment without a blocker to see if the magnet will climb up. And the result is not, so I assume that the blocker is the key parameters to cause the climbing. And I also do the experiment to put the upward force to the magnet, and the result is that the magnet will go down. So I assume that the force pull down the magnet will also cause climbing. And here's my experiment setup. And I use 1 centimeter diameter of magnet, and each of my magnet is 6 grams. And I also use motor to control the rotation speed of ferromagnetic rod, and from 30 RPM to 300 RPM. And I also use magnetometer to measure the magnetic field of the magnet. And then it's about my qualitative process. And as we can see in the video, the magnet will stick first at the rod, and when the rod is spun around, and it will spin around together, and then it will slip back to the middle part. And this phenomenon is talking about when the magnet sticks on the rod, it will add the static friction, and also it will spin around with the rod. But when we use the blocker to block the magnet, it will limit the motion, and the magnet will the static friction will transform into kinetic friction, and so the magnet will slip back. And also, there is the initial condition of the contact area, and it will at the middle part of the magnet. And when the rod spins more and more, and also the magnet blocked by the blocker, and the contact area will change besides. Like this, the blocker will give the normal force to the magnet, and then the magnet will happen the stick slip phenomenon, and so it will slip back, and the contact area will change back to the middle part. And next is how the magnet climb up. So to my explanation, that the magnet will pull down by the gravity, and then it will cause the stronger pressure at the down point of the magnet than the top part of the magnet. So the magnet will happen the stick slip phenomenon, and when it slips back to the middle part of the contact area, it will climb around the pivot point. Like this is the initial condition of the magnet, and the contact area is at the middle part of the magnet. And when it happens, when stick on rod and also it blocked by the blocker, the contact area will change beside. Like this, it will stick and the rod speed, and the contact area will change beside. And then when the blocker gives the normal force, it will slip back and then climb up around the pivot point. And this process will keep going during the motion of the magnet. Okay, and this picture shows how we just talked about to my explanation. It will pull down by gravity and have a stick slip phenomenon, so it goes up and stick and slip and goes up. And next is about my quantitative view. And here is my force analysis. That there has the friction and normal force between the climbing magnet and the rod. And also the magnet will pull down by gravity, and then it will stick on the rod because there is a magnetic force. And I will consider the number of magnets and the rising potential. And to my experiment, that if the number of magnets is less than 4, then the magnet will stick on the rod and doesn't go up. And to my explanation is that the torque of the magnetic force is much bigger than the gravity, the torque of the gravity, so the magnet will stick on the rod. And then if the number of the magnet is bigger than force, then it will go straight up. And to my explanation is that for the magnetic force will be bigger than the gravity and the friction, so the magnet will start to moving, and then it will stick slip phenomenon, and it will slip up like this. And if the number of magnets is too more, and then the gravity cause the torque will too big, then the magnetic force cause the torque, so then it will break down. So and then it won't climb up. So the number of magnets shouldn't be too many. And about my experiment, I do some parameters to explain the problem. At first, it's angular velocity. And I use motor to control the angular velocity from 30 RPM to 300 RPM. And I also control the variable of magnet amount, contact area, and the diameter of rod. And to my hypothesis that if the rotation speed is faster, the magnet will slip faster, and then so the rate of climbing will faster. And here's my experiment data that, as we can see, the 300 RPM cause the biggest rate of climbing, and so it matches my assumption that bigger angular velocity will cause the bigger rate of climbing. And next is contact area. And I control the contact area from 2 centimeters to 7 centimeters with the blocker like this. And I think my hypothesis that friction won't have relationship with the contact area, so I think it won't affect a lot to the rate of climbing. And here is my experiment data that, as we can see, the 2 centimeters to 7 centimeters is almost have the same rate of climbing. So I assume that maybe the blocker just gives a no more force to the magnet, and it will happen the stage2 phenomenon to let it climb up. And third is diameter of rod. And I use 0.6, 0.7, 0.8, and 1 centimeters diameter. And my hypothesis that if it is bigger diameter of rod, the magnet will have a bigger slip, so maybe it will have a bigger rate of climbing. And here's my experiment data that, as we can see, the 1 centimeter diameter has the biggest rate of climbing, and so it matches my assumption that the bigger diameter of rod will cause the bigger rate of climbing. And fourth is friction. And I use different tab and put it between the climbing magnet and the rod, and each tab with different friction coefficient. And my hypothesis that friction will have the same direction with climbing, so I think maybe bigger friction will have the bigger climbing velocity. Okay, and here's my experiment data. And the right side is the red tab, and it has the bigger friction coefficient. And so, as my data shows that bigger friction coefficient will cause the bigger rate of climbing. So, as assume that the friction may have the same direction to the climbing direction. So, it's the key parameters to let the magnet climb up. Okay, and here's my conclusion. And I introduced the mechanism between the climbing magnet and the rod, and I also use stick-slip phenomenon to explain how the magnet climb up. And also, I use the blocker, and the blocker is the key parameters to let the magnet have the stick-slip phenomenon like this. And also, I compare the number of the magnet and to see the gravity torque or the torque of the magnetic force, and then I can calculate that the number of magnet will also affect the rate of climbing. Like if it's too many magnet and the gravity force was too big, so the torque of the gravity force will be too big than the magnetic force, so it won't climb up, but it will break down. And about my related parameters, bigger angular velocity will cause the bigger rate of climbing. And also, the time interval between stick-slip phenomenon is smaller. Like will stick and then transform into slip, the time interval will be smaller. And about the contact area, and it won't change a lot. It won't affect a lot to the rate of climbing because the blocker just gives the normal force to the magnet. And about the diameter of rod, bigger diameter will also cause the bigger rate of climbing, and also the time interval between stick-slip is smaller. And about the friction between rod and magnet, I think bigger friction coefficient and will cause the bigger friction, and then so it will cause the bigger rate of climbing. So I think friction between the rod and the magnet will have the same direction to the climbing direction. So it was the key parameter to let the magnet climb up. And that's all my report. Thank you.
它这个方面功能。
Can you tell me where page what? Because that I think the problem thing is that we need to use a vertical rod, but in your video, like, can you show the video? The last page. Okay, I think that in the next page video, yes, it's not vertical. Do you think that they will affect the experiment data?
I think the ferromantic rod is will shake a little bit, so I think it won't affect a lot to the rate of time.
Okay, but I think that will affect the data. And can you turn to page 20? Because you say that you change the number of the magnet, but it will affect the weight of the magnet, the gravity force, but it will also affect the magnetic force.
Yes, but so I think the the delta of gravity force will bigger than the delta magnetic force. So the increased gravity force will have the bigger torque from the magnetic force.
So do you measure the magnetic force?
Yes.
And do you observe the vibration during your magnet climbing up along the route?
I observed.
Do you think that will affect your experiment?
I think no, because it is happened because of the six.
Okay, can you turn to page 41? Because you said that the vibration, you observe vibration around the magnet, but the vibration will cause the last stable about your climbing process. And can you explain like why the error bar will this be as big? It's pretty big. And what do you think that the reason that causes this error bar?
I think it's about when I track the motion of the magnet, it will have states and also slip. So the velocity.
Okay.
Thank you.
Evaluation of the opponent. The opponent takes the floor.
Hello everyone, I am the opponent Zhong Yixing from Team Votan in National Chongqing Girls Senior High School, and today I am going to oppose the problem number 4, climbing magnets. And here's the problem statement above, and we can know that the reporter limit the motion of the magnet to the vertical direction by use the blocker. So I think the setup is fixed the problem statement, but he used the but I think the rod is not vertical, so I think that will affect the experiment data. And my main focus is the climbing process of the magnet and how do the relevant parameters affect the magnet climbing. And here's the review of the report during the presentation about the theoretical model. He used a different view of the force analysis about the climbing process. And he mentioned the stick phenomenon that will that in his experiment, and I think he used force analysis to explain the whole gravity process. That's great, and mention the reason that why the magnet rotates counterclockwise. But I think he didn't consider the vibration during the quantum process and lack of the theoretical explanation. He just used the force analysis and didn't explain the force that made the magnet climb up. And about the experiment setup, he used the coefficient of friction about the blocker and the velocity of the rotation of the rod, and contact area between the magnet and the blocker and the diameter of the rod. And I think that he controlled the weight and he didn't quantize the effect of each relevant parameters. And he just used his data, but he cannot connect it with his force analysis and didn't explain the chain of it. And ignore the error caused by the vibration, because that during the short question time, I think that why the error bar is less bigger than I think that will but he say I think that is because of the vibration during the climbing process, but he think that it will affect that much. And the rod is not rotational parallel. I think that will also affect the experiment process. And about the data analysis, he observed he measured the climbing velocity and angular velocity. And I think that he explained the data with the force analysis, but he didn't explain the reason why it caused the error bar that big, and lack of the connection between the theory and the data, and didn't mention the trend of the data with the stage2 phenomenon. And I also said that I also think that there will be a critical value in his experiment. And there's the discussing point about the presentation. I want to discuss about the theory is the force analysis about the climbing process, because he didn't mention that the real reason that caused the magnet climb out along the blockers. And the main reason that caused the magnet rotates and climbing out along the blocker, while the magnet will turn counterclockwise. And how the force change between the rod and the magnet during the climbing process. And about the experiment and setup, I want to ask that how did the manipulated variable affect the climbing velocity, and how does the stage2 phenomenon happen during the climbing process? And about the data analysis, I want to discuss is the reason that caused the error, and I want to ask that the setting of the critical value and the connect between the velocity data chain and the stage2 phenomenon. And that's all my presentation. Thank you. And I want to invite the report.
Okay.
Yes. Can you turn to page 14? Thank you. What do you think that is the main reason that caused the magnet climb up?
I think it's because the gravity will cause the stronger pressure than downward, so it will have the bigger friction up, and then so the friction at the down point will bigger than the hard friction, so it will cause the driving force.
So it's because about the contact line, the normal force is uneven. You think that is?
What normal force?
But you didn't explain why the magnet climbed up, and you used the force analysis, but I didn't see any force that toward up, and that can overcome the weights.
I think it's because here will it's the blocker, and it will give the normal force, so it will also have the torque of the normal force, and so it will let it rotate.
I want to discuss the force. Can you show the first that why the magnet will rotate counterclockwise?
Here's the
Here's the blocker. Yes.
and when it's having a stick phenomenon, and having a stick phenomenon and the gravity. Okay. And so here is the normal force, right? And so here we'll have the stronger friction and up. So here is little friction. So then you will rotate.
So why cause the torque that made the magnet turn counterclockwise?
I think it's about the.
I think that is because the gravity will cause that the normal force on this contact line is uneven. So the the normal force will affect the static friction, right? The maximum static friction. So when it and about the rod will still counterclockwise, so that will cause the maximum static friction in the lower point of the contact line will be bigger.
Yes, so it means like it will be more little at the top part.
Yes, so do you think that that is the reason that cause the magnet counterclockwise?
Yes, I think it is just why I said that it will pull down like gravity, and so it will cause the down point have a bigger pressure, so it will have a bigger like this. Just why you mentioned the F, so it will cause it rotate.
So why when it rotates, why it will climb up?
Because the because like this when the contact area will change, right? So it will at the pipe point will when it change the contact area from middle part to here, and so it will have the pipe point, and then it will like the force up here, and more little the top part of the force, and so this big force, and then the pipe point, so it will rotate because of the torque.
Okay, I got it. And turn to your page page 26. Because I still cannot because you change your number of the magnet, but it will also affect both gravity force and the magnetic force, and that will if you change the magnetic force, it will affect the normal force on the contact line.
Yes.
And it will affect. Do you think that it will affect your experiment with?
Because I do the experiment with one magnet, and I use some weight to put on it, and it's 38 grams, and then it will climb up. So I think it's not no problem.
Okay, I got it. And can you turn to your page 41? I really want to discover why cause the error bar. What do you think that the reason that cause the error bar?
Maybe I think the value of my vertical axis is like 0.0.
But that is too big. That I think.
I think my value is too little, so it will cause the error bar to look very big.
Okay. So can you explain why the chain will increase?
Because because I think the diameter, bigger diameter will let the middle point contact area bigger. So I think it will cause the bigger slip of the magnet.
Why?
And because like this will contact area change between, okay, and so the rotate degree will be more big.
But I think that if you change the diameter of the rod and you fix your rotational speed of your electric drill, right? And they will also change like the contact the moment of the they will also change that the contact area per time because that different diameter of the rod.
You said the contact area is mean the rod and the magnet.
About the time that it will be the contact line, and it will move it will have the relative move between the rod and the magnet, and the contact area will be different when you change the diameter of the rod, right?
Yes.
Because you fix your rotational speed. But you said that you use this manipulative variable is to change that contact line.
To my hypothesis, that I think the bigger diameter will cause the bigger contact area.
Okay, but I think that it will also I also. And can you turn to your page 19? And do you think that the vibration will affect your experiment?
I think it will not affect a lot because I think the vibration is just a little bit, so I don't think it will affect a lot too.
But there is a friction between the there will be two friction lab between the rod and the magnet and the magnet and the blockers.
Yes.
And also I think that why do you think that do you consider the do you think that if the coefficient of the friction about the blocker is 0, does the magnet still fly out the blocker?
Yes.
Why?
Because I think the blocker just gave the normal force cause the torque, and then the magnet happen the state phenomenon. So it will, when the counter area change beside, and the blocker give the normal force to the magnet and the torque, and the magnet will slip back. And so I think the friction between the counter area between the blocker and the magnet is not very important to the.
So why you use the coefficient of friction about the blocker?
No, the friction is about the tab I put between the rod and the magnet.
Can you turn to that page?
I use a tab to put between the contact point of the magnet and the rod.
So how do you measure the coefficient of the friction?
I just calculate the tangent theta.
Okay. And can you turn to this data about you using this? And how can you explain this? Because this will affect the state phenomenon, and but you didn't connect it with your force analysis, right?
I think this is because to my force analysis, and there's the friction between the rod and the magnet, and so I think maybe the friction direction will add the same to the climbing direction. So I think bigger friction may cause the.
Yes, but if you change this, the manipulator variable, you would just only change about the maximum friction between the ferromagnet, between the rod and the magnet.
I think because I use the steady friction to explain it, because when the state phenomenon happens and when it's at the state first and it should come over the maximum static friction, so I calculate the maximum static friction.
And I also want to ask that what do you think that the relation between the velocity and your state phenomenon?
Oh, I think maybe during the motion maybe it was some lower velocity because it was stick, and also the higher velocity of stick, and it was not very.
Okay. And during the discussion, we talk about the force analysis and find that because of the friction, because of the gravity and about the contact line, the normal force will be uneven. So and the magnet will counterclockwise along the pivot, so it will tie out along the blocker. And I think that he didn't explain his data and his arrow bar with the theory, and I still cannot know that what is the relation between the velocity and the velocity and the stick phenomenon. And I also think that because there will be the factor that will affect the data is about the vibration, because that there will be the friction about the between the magnet and the blockers, and it will also cause the unstable about the experiment. And I think you should consider it. Thank you.
Okay, question from the reviewer.
Good. Greetings. So I would like to ask the reporter why the error bar is so large in the graph.
I think it's because my vertical axis, the value is too small, so you will think so that the error bar is too big.
Could you play the observation video? The first page, the previous page. Because I see there is a vibration of the block. So do you think that will impact and cause the deviation?
I think maybe it will cost a little bit, but don't think it will cost a
But
lot.
I think that will influence the contact and cause leading to the problem of whether whether the friction is existing.
Maybe I think it just because due to my experiment, the contact area with the blocker will not affect a lot to the rate of climbing.
Okay, thank you. So I would like to ask the opponent, do you think that, do you agree that the number of magnets will impact the gravity, magnetic force, and change the normal force?
Yes.
Yes, so the friction will change, right?
Yes.
Okay. And do you agree that the bigger error bar is due to the small figure in the y-axis?
I think that is because the vibration and the strut is not parallel.
Not parallel. And I see in your motor there is a vibrating. It is vibrating. I think that is real. That actually made the error. How can you say that it will make a deviation?
Your vibrating is which part?
This one. It's vibrating.
Oh, and can you repeat your question?
Do you have an experiment to back up that the vibrating didn't impact the phenomenon, the state phenomenon?
Maybe I think the vibration is just at the horizontally axis, so I think it won't affect about the vertical direction.
And could you talk more about the state phenomenon that cause the magnetic rod to rotate and go up?
Just like if this is rod and like magnet, and if it stayed on it and it was bound around with it, but it was blocked by a blocker, and so it was like this, and the contact area will change, right?
Yeah.
And so it also pulled up by gravity and caused the torque, and then
Torque from what?
From gravity and the magnetic force, and so it will have a pipe point, and when it slid back, and it will climb
So
around.
will the friction cause the torque?
Yes.
Yes. And so it's go up, right?
Yes.
The friction torque will go up.
Yes.
Okay. And thank you.
Alright, so after review. Reviewer takes the floor.
Greetings, I'm the reviewer from Ridiculous. Today I'm going to give a review about the number 4 question, flying magnets. So in the previous discussion, there is a comment for reporter. The pros will be full explanation to the phenomenon, and then they classify different situations to explain different mechanisms. And there are also some cons that the areas for improvement, like utilizing hand to conduct experiments, a lack of mathematical evaluation for the data, and didn't mention how to measure the coefficient of friction. didn't fix the magnets on the vertical direction well. Some theories not correspond to the experiments didn't manifest the research of the rotation, confusing description, and the time will vary the distance between magnets and the rod and make the magnet force different. And about the comments for opponents, the pros will be perspicacious, sagacious, innovative, and also they understood the experiments. And they stress on the data analysis. But they lack of inquiry for the classification. So here is the previous discussion analysis. When it comes to the stability, the rod isn't always vertical, the magnet will vibrate. The opponent said that. And reporters say it doesn't matter. We agree with the opponent, the vibration may impact the slip and slide motion in the theory. And when it comes to the control variable, the opponent said that when the gravity increases owing to more magnets, the magnetic field also increases. And the reporters say that the impact from the gravity overshadows the magnetic field. We agree with opponents. There should be only single independent variable in an experiment, or L is meaningless. Because in this experiment, the friction, the normal force, the magnetic force will change, and also the gravity. And there is a point about the fundamental mechanism. The point say that after Melanson, the magnets climb up. And the report said the friction and the normal force and gravity will create the torque so that it will rotate and go up. We agree with the reporter. Friction is one of the explanations. Nevertheless, we suggest the reporter to mention details further. So in the previous question, we asked about the big arrow rod, and the reporter said that the vertical displacement is too small, and the opponents talk about the instability, and we think that the instability of the mechanism that's shown by the reporter actually caused the deviation in the experiment. And also, when it comes to the previous experiments about the independent variable of the number of magnets, we think that because the gravity, the magnetic force, and also the friction will change. So actually, the slip and stick phenomenon will have changed. And in the previous question, we asked, did the vibration of the black matter? The reporters say that no, since they have verified the area of contaction doesn't matter, and the opponent didn't ask it. And we think that they said the contact area will move, but actually, if the contact area begin no contact with the rod, and the normal force will become zero, and the friction will not have the torque to make the magnetic rod to climb up and rotate. And that will be my review. Thank you.
Concluding remark from the reporters.
Hello everyone, I'm the reporter from Team Bernoulli, and here's my concluding remark. And first is about the stage-slip phenomenon, and I use the stage-slip phenomenon to explain how the magnet climb up. And also, my explanation of climbing is that about the gravity, torque, and also the torque of the magnetic force. And about the force analysis, I use the magnetic force, gravity force, and the friction to explain how the magnet climb up. And about the different parameters, I do the angular velocity and diameter of rod and contact area to see how it affects the rate of climbing. And about the friction and the gravity force, I think it's also both important parameters to affect the rate of climbing. And it will also cause climbing too. And about the data analysis, I think the error bar may be affected by the vibration, and so I think the opponent and the reviewer make sense. But I think also, and I think just while the data shows that my vertical axis is very small, so I think maybe the error bar will not very big. So yes. About the discussion, I think that the reason of rotation in the discussion is about the gravity cause the down point of the magnet have the bigger force than the top part, so it will cause the torque to let the magnet rotate up and it will climb up. And about the importance of friction and also the diameter of rod of the contact area with the magnet, and then the vibration. I think I observed that, and maybe I can consider it in the future. And about the friction between the rod and the magnet, and I think I don't explain very clear, and it is about between the timing magnet and the rod, and I use a tab to control the friction coefficient. And about reason of error bar is that just what I mentioned. And about stick phenomenon is the key point to let the magnet climb up. And the blocker shape maybe will affect a little to my experiment data. And that's all my thing.
Okay, question from the jury.
We will want to have some object move. We have to exert a force onto that object, right?
Yes.
Where is that force moving the magnet upward?
The thing is about when we rotate the ferromagnetic rod, and the magnet will press the blocker, and blocker will give the normal force to the magnet.
But actually, without the blocker,
It won't climb up.
it will. It can climb up as well.
I think the friction will cause the torque and make it to rotate and climb up.
No, rotation doesn't necessarily lead to the motion, the upward motion of the magnet. The rotation doesn't really move the upward, make the magnet moving upward. So, what is the force? The
Friction. Friction between the contact outlets.
Without rotation, you also have that friction. But that friction doesn't move.
I think maybe it's about the gravity.
Sorry,
Gravity force.
the force of gravity
Yes.
points which direction?
It pull down the magnet.
So you will make the magnet move.
Yes, because I do experiment to put the upward force to the magnet, and then the magnet will go down.
I'm sorry.
I put the upward force to the magnet. I use the string to pull the magnet, and the magnet will go down.
So I don't know if I missed anything, but did you measure this climb up distance or climb up speed versus this rotation of this magnet?
I didn't calculate the exact.
Did you measure? Did you find any correlation?
I use tracker to track the time interval between the 30 RPM to 300 RPM.
So during this climb up, do you think this magnet rotation is a pure rotation?
Yes.
It's a pure rotation. Do you know what that means?
Yeah. The angular velocity will remain the constant.
That's not what it means.
So can you repeat your question?
So during this climb up, does the magnet actually is a pure rotation? That means that does it slip on this rod?
I think the stick phenomenon is about the horizontal move, about between the ferromagnetic rod and the magnet.
So you think in vertical direction there's no slip?
No,
So it's a pure
because it
rotation.
is climb up along the pivot.
Any more questions? Okay, thank you. So now it's time for the jury to score. Ready? Okay. Score for the reporter. 67777. The score for opponent. 67686. The score for reviewer. 66676. Okay, thank you, and now we'll have a break.